Hello, everyone. So today I'm going to talk about a very recent Putnam problem. And the reason I decided to talk about it is, well, I think it is really nice, and you will know why later. So what is the statement of the problem? So basically, it asks us to find like all the positive integers and such that when you multiply the numbers from 1 to 3 4 all the way to n times a number m, where m is relatively prime to n, you can always find a permutation that takes the set 1 to n to the same sets 1 to n, such that m's times k is the permutation applied 2 times. And to see what the goal the roadmap of the problem it is, right? So first of all, we need to know like, okay, why how does like multiplying a number relate to permutation, and how does that relate to permutation applied 2 times? And the other one is to, well, really understand like what can you do with permutation itself, and then finally to solve the problem. So I would say the roadmap today is the following. The first one is to understand permutation, and then the second one is that what permutation is other permutation twice, and then the third one is to find all such n. Okay, so the first thing we are going to do is to understand permutation. Why does this even matter? Because we want to link like multiplying k to mk versus a permutation, say like pi square of k, and so like i.e. like how are they going to relate to each other? So the fact is that, okay, so right now we have the fact that GCD of mn equals to 1, and the fact is that say we have a function equals to mk mod n. This rho is a permutation, meaning that so what does that mean? You basically have that this one, rho 1, rho 2, all the way to rho n, which is like, m 2m blah 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 mn mod n. This is 1 2 3 all the way to n in some order. So okay, sorry, this is bad handwriting. So what this means is that km, uh, if km is the same as lm, sorry, I think I should really write km equals, oh yeah, okay, sure, this is correct. If km equals to lm mod n, then you basically have k is the same as l mod n, which also means that k equals to l if they are both in the range of 1 to n. So now the question now becomes that, okay, since this one is already a permutation, when can this permutation be written as twice of another permutation? So in order to understand this, we need to understand we need to see like permutation in some other angle, which is which is basically permutation as sorry, not set. I would say disjoint union of orbits, or if you like, you can call it cycle. So how does this even how does it even work? Say let's say we have like n equals like one uh, n equals to 3, so we only have like 1, 2, and 3. So the identity if the identity permutation will basically be like 1 goes to 1, 2 goes to 2, 3 goes to 3. So meaning that we only have, each of them is uh, from its own cycle. Now how about things like like 1 goes to 2, 2 goes to 3, 3 goes to 1. That means that you have this cycle of a 1, 2, 3, and then go back to 1. So you have this 1, 2, and 3. And finally, what happens if you say like 1 goes to 1, but you have like 2 goes to 3, 3 goes to 2? Then if you applying this permutation to 1, you get like 1, you just keep getting 1, whereas 2 and 3 just alternate among each other. So this is one cycle, 1, and then 2 and 3 forms another cycle. So why does this why does this work? Because now we can see that if let's say we have pi as one of the permutations, we can see like if we do the cycle decomposition of pi, then we can easily see like what is the cycle decomposition of pi square. So let's say we have uh, so let's say now I give another example, say n equals to 7. So and then pi is basically let's just say pi is like 1, 2, and 4, 3, 6, 5, 7. Meaning you have like pi 1 equals to 1, pi 2 equals to 4, and then pi 4 equals to 2, and then pi 3 equals to 6, and the list goes on. And then 7 goes back to 3. Okay, so how does pi square work? Well, if we apply pi 2 times to 1, you get back 1. If you apply pi 2 times to 2, then 2 goes to 4, 4 goes to 2, so you have like pi square 2 equals to 2, pi square 4 equals to 4. And then here you basically get pi square of 3 equals to you jump 2 steps equals to 5, and then pi square of 5 equals to 3 because it goes 2 steps, and then similarly 6 and 7 are also to 6 and 7 also go from one to the other. So the thing is that this thing, well, you can always show that this is also another permutation. And now the orbit basically becomes 1, 2, and 4. It just split up into 2, and then 3 and 5, and then 6 and 7. Okay. So now the question is that given I would say this can be written in red. Okay. Question. Given permutation rho, does there exist pi such that pi square pi equals to does that exist pi such that rho equals to pi square? Yeah, it should be this way. Okay. Now the answer is that, well, it really depends on rho. So let us go back to here. So here we see that this is how this pi square should be given that pi is in the earlier form. So what we see is that for this odd cycle where we only have one element, you still retain the same element. Whereas for all the even cycles, it got split up into 2. Now this is also true in the sense that like from pi to pi square, odd length cycles re, uh, remain, but could be shuffled. So let's say you have like 1, 2, 3, it will become 1, 3, and 2. Whereas even length cycles got split into 2 in an alternative fashion. So meaning that let's say you have just now we have this like 3, 6, 5, 7, it becomes so 3 and 5 the odd index will go to one set, whereas the other one will go to the other. So the claim now is that The claim now is that um, all even length. Okay, sorry, this shouldn't have a quotation mark. So all even length cycles can be paired up cycles in, which also means that hmm, which also means that for each k even, the number of cycles with length k in pi square is also even. Well, why is this the case? Because let's say that we have pi square equals to this, revisit our pi square before. So here pi square, we see that the uh, after this two four is split into two and four separately, then each of them becomes length one. So okay, sure, this doesn't matter. But then here we have start with length four, and then here we have a length two and length two over here, and you can see that there's you can see that there's that there's a pairing in that among them, in the sense that, well, you know, you kind of know that these two must come from the, well, from the same cycle in pi. Well, it does okay, so in general this doesn't it doesn't really matter, like, okay, like which two should be paired together, but then the point is that um, cycle of length k even must, okay, in pi square, must come from some cycle of length 2k in pi, and therefore it should have another partner, and therefore you can think of it this as a notion of pairing up. So the so so the so now this becomes that if rho equals to pi squared, then uh, all k for all k even number of cycles with length k. I feel like at this point, let's might as well give it a variable names. We call this like n row of k must be even, and so this kind of limit the condition that this row must satisfy. Now, is this sufficient? It turned out that yes. So turns out this is already sufficient. And why is it so? Now, okay, let's see. But why sufficient? So say rho has this rho has this condition. Now let's say for each even k. So let's say k is even, and then basically you have the n row of k is even. So meaning that you can pair them up. Uh, so each of them has length k, and then you pair them up. Each of them has length k. So meaning that each of them is each of them is a cycle of row. Then how do you reconstruct the cycle of pi then? Well, what you need to do is to merge these two together and then repermute the numbers in the, sorry, like order the numbers in an alternating fashion. So what this means is that let's say you have like 1 2, 3, and then the other one is 4, 5, and 6. And then you want to merge them together. So what you would do is that 1, 4, 2, 5, 3, 6. And you can show that if this is pi, right, then row will be split into 1, 2, 3, and then 4, 5, 4, 5, and 6. What happens if for k odd, then we don't know what this would be. So as it turns out, we already see that it is possible to retain this this sorry, it is possible to retain this cycle for the original pi. It's just that you have to repermute the numbers again. So let's say what I mean for this is that let's say you have cycle of pi. Okay, I will say retain but shuffle. Let's say it is 1, 2, 3, 4, and 5. And then what would happen is that so here it is 5, right? Now that the length is 5. So we know that 5 plus 1 is divided by 2 equals to 3. So what you do is that you jump 3 steps in order to get to get pi. So 1 jump 3 steps becomes 4, and then you jump 3 steps for 5 1, and you get 2 back, and then jump 3 steps 2 3 4, it becomes 5, and then it becomes 3. So this is how I should say this is row, and this is pi, so that you get row equals to pi square. Okay. So this is so this gives the conclusion that uh, for permutation permutation row, that exists pi such that is equals to pi square if and only if for all even k, the number of the cycle of length k in row is even. And therefore, the n we are looking for is such that for all m such that GCD mn equals to 1, if row row is such that row m equals to row k equals to mk, then row has this property. Okay. Okay. So now we talk about what are the suitable ends. So in order to do that, we kind of if we want to try manually, we kind of have to try all m such that the m is relatively prime to n. So for example, like if say like if n equals to 1, then the only thing that we can try is m equals to 1, right? So this is the only permutation, and therefore this n equals to 1 works. N equals to 2, well, we only have m equals to 1 anyway. So m equals to 1, we know that mk equals to k, so this this is the identity permutation. So which means that you get this as the this as a cycles. So you see that all the cycles have length 1, aka the even length cycle. There's 0 of them. So this also works. Now n equals to 3. Well, we are not going to try m equals to 1 anymore because it's just going to be identity. So let's do m equals to 2. So when m equals to 2, you see that 1 becomes 2, 2 becomes 1, 3 becomes 3. So you basically get this cycle. Now see that we only have one cycle of length 2. So this is a no. when n equals to 4, now m equals to 3 there, right? Then uh, you see that 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4. So this also gives 1, 3, 2, and 4. So again, there's only one cycle of length 2, so this cannot work either. And it now seems like we are doing all those, like either those like those little experimentation, which there are a lot of them that, and then you don't even see where I'm leading to. So I'm just so let me just tell you to hanging a bit, hang in a bit, and let's see what we can learn from all those like little permutation, all these experimentations. So so when n equals to 5, right? So let's just say well, let's just say m equals to 2. Why do I choose m equals to 2? Well, I will talk about it slightly later. So you see that 1 goes to 2, 2 goes to 4, 3 goes to 1, and um, 4 goes to 3, and 5 goes to 5. So now you see that we have this 1, 2, 4, 3 cycle and 5 itself. So this has length 4 and it is alone. So we cannot accept this either. N equals to 6, this is interesting because m equals to 1, we already know that this is the identity. It is not gonna pass. Well, 2, 3, 4 are not relatively prime to 6. So we only have m equals to 5. So let's see what happens. So 1 goes to 5, and we also know 5 goes to 1. 2 goes to 4, and 4 goes to 2. 3 goes to 3, 6 goes to 6. So you have 1, 5, 2, 4, 3, and 6. Okay. So this we can see that there are a good pair of this together. So this will work. Okay, now let us stop over here. So one thing that you can see is that first of all, trying m equals to 1. Sorry, m equals to n minus 1 is a good idea, but doesn't always work. Okay, and then the second thing is that for n equals to 5, you see that we try m equals to 2, and there is a reason. Well, you see we can see that if we try m equals to n minus 1, right, then you don't see a counter example, meaning that the number then that row will basically have fulfill the condition we want. But why m equals to 2 and then 2 though? Now we can see that here there is like a complete cycle except n itself. Okay, so so this brings to our topic. So you see that okay. So why is this possible for 5 and not for 6? Well, 6 is not prime, whereas 5 is prime. So for 6, right, this 1 and 5 they are the only numbers that are relatively prime to n. So they have to form their own cycle, even whether they are together or they are not together. They have to form their own cycle, and they cannot mix with, say, like 2, 4, and 3. And there's just simply no way. But other than that, we see that since n is prime, we can choose m equals to, say, m equals to the primitive root. So what does this even mean? This means that m to the power of k is congruent to 1 mod n, implies that k is divisible by n minus 1. Okay, so in this case, we have like we have that this n, and then 1 all the way to n minus 1 in some order. So here you have a cycle of length n minus 1, just one cycle, and therefore you know that this is not this is not going to work. But what happens if n is not prime then? Okay, so this is just the roadmap that we are going to do. Okay, so recall that we have this roadmap from just now. We know that n equals to prime is going to be out, well, except for n equals to 2 just now. And but how about n is not prime? So in general, as I say, that we can first try to see like what happens if m equals to n minus 1. Then we see that then we see that rho of k equals to n minus k, whereas rho of n minus k equals to k. Okay, so what this means is that n and maybe n minus 2, if n is even, will be in their own cycle, whereas for the rest you basically have k and n minus k in its own cycle. So this k is going to be 1, 2, all the way to, what was that? And the floor function of n minus 1 over 2. So this means that we require the floor of n minus 2 or n minus 1 over 2 to be even. So meaning that n has to be congruent to 1 or 2 mod 4. And this itself is pretty, I would say it's already a pretty good progress, because the next thing I'm going to show you is that we can treat each of these separately actually. So it turns out that in most cases, this is going to work. This is not going to work except n equals to 1. Now, how do we how did I come up with this this thing with like with this much confidence? Well, I would say that that there are a lot more try and error that I've done. So how to get there? Well, you basically have to try, like, say n equals to 9, 10, and then 13 is a prime, so we don't have to, and then 14, and then and maybe and even things that are the things that go to 18. So what you will see is that even for 10, you will see some patterns. So for example, for 10, right, you see that m equals to 1, 3, 7, and 9, and each of them will each of them have their own like when you try them, then you get some interesting observations. But the TLDR of this is that when n is congruent to 2 mod 4, all cycles can be paired. So what does this? What do I even mean here? Regardless of m. Okay, so what do I even mean over here? So if we go back to the say n equals to 6, right? Then you see that 1 and 1 5, we have this 1 5, and then we have 2 4. So we have this 2 cycles of length 2, and it turned out that 3 and 6 can also be matched to, with each other. So this so the claim here is that when n is congruent to 2 mod 4, let rho be the permutation such that rho k equals to mk, and then GCD of mn equals to 1, so they are relatively prime to each other. Then this one is even for all k. So we call that this is the number of cycles in this permutation rho of length k. Okay. So how do we so how do we get there? So first of all, right, we see that since this n is going to this n is odd, meaning m is even. So m is sorry, so n is even and m is odd. So k is odd, then row of k is odd. K is even, then row of k is even. Okay, so meaning that like consider any cycle. If this is odd, right, then the whole thing is going to be odd. If this is even, then the whole thing is going to be even. All right, and turn out that we can try to map this according to according to this pattern. So so again, like what do I even mean by this? So let's say we let's say we have an odd cycle. Say so I mean I don't mean odd cycle, but I mean cycle where elements are odd. So say we have so we have something like A1, A2 all the way to AK. Now how are we going to map them? Well, it is pretty natural to think that the other cycle is going to be 2 times A1, 2 times A2 all the way to like 2 times AK. But is this even is this actually rigorous? Well, we will have to show that. Now, turn out that turn out that this one A2A1 2A2 all the way to like 2AK are all different. So okay, so first of all, we all agree that row of like 2A1 is going to be 2A2 because 2A1 times what's the number m equals to 2 times A1m equals to what? And then this is going to be A2. And also things like if n divides 2A1 time minus 2A2, say like 2 AI divide if let's say 2AI and 2AJ are the same thing, so meaning that 2A n divides these two, that means that and okay, so we know that n is even, so n over 2 has to divide 2A1, has to divide AI minus AJ. Okay, so now the next thing is the next thing is that so this one is odd, this one is odd. So this difference is going going to be even, and then and then n over 2 this is odd, right? So since we have an odd number dividing an even number, that means that n also divides this thing, and therefore AI equals to AJ. And since AI and then since we have the cycle to start with, that means that I equals to J. So meaning that uh so meaning that 2AI all the way to like what, well, how many numbers we have over here, 2AK are all different. So the mapping is legit. So the conclusion is that n equals to 4k plus 2 works. Okay. Now now to recap, right, we have already shown that n equals to 4k plus 3, 4k plus 4 doesn't work, and because of m equals use m equals n minus 1. N equals to 4k plus 2 works. Just pair the cycles. Now we are left with n equals to 4k plus 1. So how do we do that? Okay, as we have mentioned just now, so we have already shown for different cases except n equals to 4k plus 1. So it turned out that this is the trickier part. Well, the solution, of course, to deal with this, of course, generalizes for all the odd numbers, but it is also a bit tricky on how are we going to proceed with this. So we call that when n equals to prime, n is a prime number, then we basically use m primitive root. Now n is not prime, so, and therefore there's no primitive root, which is sad. Okay. Well, okay. Sorry, I kind of lied a bit. So, and if n is not prime, right, then and not a prime power, then there's no primitive root. Okay. So what we could do here is that we can consider the prime factorization of n, and then take the primitive root of all the of the of each of the each of the prime powers. So we call that primitive root exists for all prime powers. Okay, so what we could do is that n equals to prime factorize, and then choose mi equals to as one primitive root of this guy. Okay, since we already know that like n is odd, right? Then all these numbers are all, I should say, all odd prime powers. Sorry, yeah. 2 to the power of k does not have primitive roots. Okay, so choose mi as primitive root of this guy, and hopefully can we choose m congruent to mi modulo, say like pi alpha I. So turn out that this is possible because of Chinese remainder theorem. Okay. So now, how are we going to how are we going to proceed next? So it turned out that this M would work, but we have to show that there are a lot of other things that we need to show, because well, for one thing, that there the so for one thing, the cycles that you have shown, right, it could be that they are also like split into like some smaller some smaller decomposition, or maybe there's some duplicates, so that would invalidate our claim that this end does not work. So the thing, how are we going to show is how are we going to show it works is that, well, we will just show that, like, okay, so we will just show that beside the sequence, sorry, beside the number n, which will form its own cycle, the next one will have the next smallest cycle will have even length, and there will only be one such cycle of the such length. So what do I mean by that? Okay, so now the focus is that why this m is a valid counterexample for n. Okay. Okay, so if we think about it, right, so what happens to m? What's the cycle of this k? So we want to find like what is what so what okay let me rephrase. One thing we want to see is that rho to the power of jk is the same as m to the power of j times k, and we want to see the minimum j such that m to the j times k equals to k mod n, and this j, this one is going to be the length of cycle. Okay, so we already see that this so for example, like when k equals to n, right, then we just then we simply have like j equals to 1. But for other j, then since this m is a primitive root, then this is not then this is not going to be have length 1. So so say so let's just that so what happens in it, and i.e. like how are we going to proceed with this? So turn out that we need to see like what is the GCD of k and n. So we need to study this thing. Okay. So one thing that we can think of is that when the GCD of this guy is say like say if GCD of k and n is equal to 1 1 for example, then we basically need this m to the j equals to 1 is necessary, and this would force j equals to phi of n. Yeah, I think it should be phi of it should be phi of n. Sorry, I mean, okay, sorry, this is not sorry, this is not correct. J is not going to be phi of n, but j is going to be the LCM of um, phi of p1 alpha 1, phi of p2 alpha 2. Okay, because because it is the primitive root of each of those. Now, notice that this is still a bit tricky to work on because, well, as I have mentioned that if we go with this, that it is inevitable that we might have like some other like some other cycles in of the same length. And so what this means is that even you have this many numbers that are relatively prime to n, because of this thing, that it does not necessarily multiply to phi of n. You might have different sorry you might have different cycles, which I mean uh, which are basically those numbers, and there might be just even of those. So a smarter way, which I mean, it also took me a while to think of, is since GCD kn equals to 1 is not possible, how about if GCD of Kn is as high as possible, but not equal to n. Okay, so how does this work? Well, this means that GCD of Kn is n over p, and this p is the smallest prime divisor of n. So it just is. So first of all, it turns out that this the length of cycle is going to be p minus 1. Well, again, because of m is primitive root. Now, one thing that one other thing is that it, length of other cycles is greater than p minus 1. Well, by other cycle, I mean excluding n itself. So why is this? Why is this so? Because you see, we see that mj equals so let's say m times p to the p minus 1 times k is congruent to k, meaning that k times m p minus 1 minus 1 is equal to 0. Okay, so first of all, since m is a primitive root of everything, right? Then this one is divisible by p for sure, but not p square. While assuming that n has a higher power, and not other q where this is the other prime divisors. And since this is the case, then we need GCD of Kn must be equal to P, and then then there are like P, there are P minus 1 of them. So this will form its own cycle. So that means that n of n of this row of P minus 1 equals to 1. So this already gives a counterexample. All right. So that means that all odd numbers can work. Well, those greater than 1 cannot work. So to summarize, these are the following steps in solving this problem. Now, the first one is that recognize that the mapping k to mk is a permutation. So let's say that this permutation is given by rho. The second one is that there exists pi such that rho equals to pi square. Well, okay, this is permutation. If and only if uh, for all even k, the cave length cycles their for all even k, there are even number of k length cycles. So this basically means that we need to see permutation as um, as the disjoint union of cycles. Okay, and then the third thing is that the third thing is that while we try m equals to n equals to 1, that eliminates multiple of 4. Well, technically 4k minus 3, but we can also use the method for other odd numbers to eliminate that. And then the fourth one is that when n equals to 4k plus 2 works, you know, that way we just do mapping, or like say like pairing of cycles via like AIs to 2AI, where this is odd. And then 5, for n odd, where n is when n is greater than 1, we use m primitive root of all the prime powers dividing n. Okay, and then show that only one cycle of length p minus 1, p the smallest prime divisor of n. So yeah, so basically this is the summary that uh, we went through for today. So I would say that this is a pretty nice problem. Well, it is a nice combination of both combinatorics because permutation and also number theory. Well, because it also involves something that some things related to primitive roots. And in fact, it's at one point I did like after say like I think like 10 to 20 threads, if not mistaken, on art of problem solving. Uh, I would say all the solutions that I've seen use some sort of what use some sort of primitive roots. So this for especially for the odd case. So yeah, this is something that I really appreciate because there's like enough concepts or enough techniques that are being combined together and yet without making it ridiculously difficult to solve. So yeah, that's all for today. I hope you enjoyed this walkthrough. Thanks for watching.